Carrier frequency synchronization is required in passband modulation schemes such as QAM and PSK. The receiver local oscillator is not frequency and phase aligned with that of the transmitter. A carrier frequency offset, abbreviated as CFO, usually arises due to two reasons: frequency mismatch between the transmitter and receiver oscillators, and the Doppler effect. We will discuss the Doppler effect later during the wireless channel. This is a block diagram of a QAM transmitter and receiver for a quick overview, and we can see that the data symbols are upsampled before pulse shaping and then upconverted through the local oscillator and sent on the wireless channel. At the receiver, they are downconverted before match filtering and then downsampled to one sample per symbol before mapping onto the receiver constellation. Let us see how carrier frequency offset affects this process. But before that, we need to know what a ppm rating is that is usually mentioned with the crystal specifications. Basically, it indicates how much the frequency will deviate from the nominal value. ppm, as the name says, is parts per million, is 1 out of 10 raised to power 6 parts, just like 1% is part in 100. So for example, if we take a wireless system operating at 2.4 gigahertz ISM band and plus minus 20 ppm crystals, the maximum frequency deviation becomes plus minus 20 parts per million multiplied by 2.4 gigahertz, which is plus minus 48 kilohertz. If the transmitter is at one extreme and the receiver is at the other extreme, the total frequency difference can be 96 kilohertz, which is a significant value. There are three scenarios that need to be considered to understand the effect of a CFO. If it is so large that the received signal falls outside the bandwidth of the analog pre-filters in the front end, then this is a case of a bad system design and nothing can be done in this regard. In case 2, the received signal has a CFO which is within the bandwidths of the analog pre-filters but significantly outside the bandwidth of the match filter. In this case, a reasonable amount of energy is filtered out and we cannot downsample the signal to one sample per symbol after match filtering. In case 3, the CFO is relatively much smaller. We can downsample the signal to one sample per symbol after match filtering, and there is not much loss in this process. Here we can apply symbol rate techniques. Here we need to apply frequency estimation techniques that operate at L samples per symbol, and here we need to redesign the system. So for example, if the CFO is small, which is case 3, then there is no change in magnitude, and just like the phase rotated the constellation, a frequency offset keeps rotating the constellation, which means the constellation is spinning in a circle. This is an example for a 4 QAM system, and this is an example for a 16 QAM system.
In this flow graph, we want to see what the carrier frequency offset does to a received QAM constellation. Although we already discussed this concept in a little detail in lecture 5, where we saw that a phase offset rotates a constellation by a certain angle and a frequency offset keeps rotating the constellation in a circle. Here the effect we will see in a different light, in that we will vary the spectrum and see how far it goes. So this is again that ID and the title. The frequency offset, let's take it from minus 5000 to 5000 Hertz. Excess bandwidth is given by 1. You can always change this value later. I'm showing it as 1 here so that we can clearly isolate the effect of carrier frequency offset from other variables. The samples per symbol is given by 16 and the sample rate is 48,000. The carrier frequency chosen is 6000. It's not very high so that we can clearly see the spectrum shifting. This is the bits generation process, and this is the custom QAM waveform block where we have chosen the excess bandwidth, sample rate and samples per symbol. However, the carrier frequency introduces an additional factor, which is frequency offset. This is the local oscillator I and Q arms, and they downconvert signal to baseband. The flow graph looks a little cluttered, but this is just flowed to complex and the frequency sync so that we can see the received spectrum before down conversion. Then we can see the received spectrum after down conversion. So we can compare the two as well. Here we have a noise source because it has a flat spectrum, and when this is given as an input to a root raised cosine filter, we can clearly see the match filter spectrum along with the down converted spectrum. This we will see when we run the flow graph. Finally, these are the match filter in INQ arms and the downsampler in INQ arms, which throw 1 out of every samples. So 15 out of every 16 samples are thrown. So we say that they are down converting by 16. And then the oscilloscope plot, and then we have a scatter plot and the frequency sink. Let us run the flow graph and see what the output is. Here we see that the downsampled symbols in both INQ arms are perfectly mapped to their binary representations. This is why we have a perfect scatter plot here as well. And then observe the receive spectrum. Since the signal is real, we have a symmetric spectrum around frequency 0. The down converted spectrum is basically, this is minus 6 kilohertz, this is minus 12 kilohertz. Shifted the whole spectrum by -6 because it was a complex sinusoid. It was both in INQ arms combined. The frequency at 6 kilohertz, it has come down to 0 kilohertz. And the filtered spectrum after the match filter is clearly seen to be shaped by the match filter, while this part is filtered out, the double frequency term. Let us see what happens when we introduce a carrier frequency offset. So first thing is that the scatter plot starts rotating as expected. The second thing is that if you see it clearly, this is what I wanted to do. You can clearly see that if the symbols were all ones or all minus ones, we can see a carrier frequency offset riding on the data symbols. This is a very interesting part. From the spectrum, we can see here that the match filter and the incoming spectrum are not completely overlapping anymore. As discussed in the text in the lectures, we keep sliding the frequency offset, which means for a larger and larger frequency offset, the incoming signal energy starts getting filtered out by the match filter. Therefore, our limit, which is around 15% of the symbol rate, below that we can downsample the match filter output to 1 sample per symbol and still recover the carrier frequency. After that limit, even the spectrum is sliding past the match filter due to the carrier frequency offset, the signal distortion becomes apparent. And then downsampling to 1 sample per symbol does not remain viable. Now we have to downsample at a certain number of samples, like 4 or 8 samples per symbol, so that we can recover and compensate for the carrier frequency offset. The filtered spectrum also starts to lose its shape and distortion is quite visible here. This process goes on. Observe this incoming spectrum sliding to the right and the signal energy being filtered out by the match filter. Here the spectrum is completely filtered out.
The big picture follows from the last slide. For case 2, when there is not enough overlap with the receive filter of the incoming signal, then we cannot downsample the signal to 1 sample per symbol. We say that this is a non-timing aided case, and since the timing is not available, the data is not available. Remember that data is only available at 1 sample per symbol after the timing is recovered. Otherwise, we do not know which sample corresponds to our modulation symbol. When the CFO is small, then we have a timing aided case where both data aided and non-data aided case are applicable, and our algorithms will operate at L equals 1 sample per symbol.